Hey guys, this is lesson 12, and I'm going to link something on the bottom that's going to be super useful if you can make sense of it. I don't know if it makes sense to me, like only to me, but I'm hoping it makes sense. It's like the trends. So there's different things that I've figured out. So I'm just going to be referring to that. I can't pull it up here because it won't let me show it in a Word document. So I'll just kind of try to walk you through it. So basically what I see here is that we're going to have 6 pi rings. So I'm going to look in my little trend thing that I'll have down below, and I'll go to 6 pi, and then I see we're going to have light, so I'll go to the one with light, and mine says same conformation or only center number is different, but I see that my first number is different, so I'm going to go with the opposite. So I think it'll make sense. It'll make more sense if you see it. But basically what I have, if all this was the same, they were all Z, then the methyls would be trans. But since they're not, the methyls are going to be cis. And if you've done this homework a lot, you can kind of do it, but I'll show you shortcuts at question 5. So let me just draw this. What is it? 8. 1, 2, 3, 4, 5, 6, 7, 8. We got a double bond here, double bond over here, not like that, and a double bond here. Now I'm going to try to move everything around, so let's see. 2 is going to be E, 4 is going to be Z, and 6 is going to be Z as well. I'll add my hydrogens, hit arrange and fit. And he was moving everything around. I just find it easier to, basically I'm going to move this bond, attach it to this one, so that the 2 methyls are sticking out, and then I'm going to move this bond, and then move this bond. So there's going to be 3 moves total, I believe, and it's going to give me a cyclohexene ring. Let's see, I'm going to grab the bond so I'm grabbing the bond from here to make sure that this outside carbon gets connected over here. If you grab it on this side, it's going to connect this carbon and you're going to have a 5-member ring. So I'm going to make sure I grab it right there, place it onto this carbon that has a double bond. I'm going to roll this around, and actually I'm going to press arrange just so it's kind of in a ring already. Okay, so I want to get this double bond and move it over here, and then I'm also going to move this one, so it's kind of like a shift of electrons. Arrange, fit, and roll. And then looking at my chart, I said that the same conformation with 6 pi bonds and dealing with light would give us trans. We don't have the same ones, so that's going to give us cis. So when I say that, I mean that these methyls are going to be on the same side. So let's see if that comes out right. I come out with these trends to try to figure out what's like a foolproof way to do it. So far it's worked for me. The only ones I haven't been able to figure out is when they're all E, and I'm thinking that when it's like that, it's okay, let me just do this way. When it's like that, I think it's going to stay as a chain, because when you have an E conformation, it's more stable than being in a ring. I'm thinking. I haven't really figured it out, but I will figure it out. Okay, I have my cyclobutene ring, and then it's going to react with heat. So this is just going to make a chain. I'll go ahead and move this bond over here to this carbon, move this one over here, hit arrange. And let me see if I have this in my notes. Okay, yeah, this is one that he went over in his video. So you're just doing the opposite, you're making the chain. Okay, product of buta-1,3-diene and light. So when you have light, you're gonna make a ring. When you have heat, I believe we're going to leave it as a chain. It was kind of hard to make notes on this because there's just a lot of writing, so I don't have that many notes, so I'm kind of just going off of feel. So 1, 2, 3, I got a double bond at the 3 position. I'm gonna add my hydrogens. Okay, I'm thinking if this was E, then maybe we would leave it, but let's try it. So I'm gonna use my heterolytic function, and I'm gonna grab this bond, put it over here, and then grab this one, shift it over. So it's gonna give me a little like box ring, and let's see if that is right. Okay, so yeah, with heat, I know when you have the butadiene, you wanna just leave it like that because you really don't want the 4-member ring. But with light, it's a little bit different. Okay, so this is a really long one. They're all the same, so I'm gonna look on my little chart, and I have same conformation, and then I'm gonna look for more than 6 pi, because I have 1, 2, 3, 4, 5, 6, 7, 8 pi bonds. So more than 6, and then I'm dealing with light, so I know that this is going to give me cis methyls. So there's a little shortcut. I was gonna wait later. I'll do this one like a shortcut. So basically we're making an 8-member ring consisting of 3 double bonds, 2 methyls on the bottom, away from that top double bond. Add our hydrogens, hit arrange and fit. And then when I saw in here, it was same conformation, more than 6 pi bonds, and dealing with light gave me cis methyls. So I'm going to roll this around, and I see that my methyls are not cis. I'm going to wait for that to arrange. And then after it arranges, I'm going to move my hydrogen down and my methyl up on the right side. Okay, so I'm going to move this hydrogen down, move this methyl up, so that the methyls can be at the same position as each other. This is a little shortcut because the decas are really long, and I don't really like to deal with them. Again, I don't know what happens if they're all E. I think they would stay the same when dealing with heat. Okay, so this is, I'm gonna look on my chart. This is the deca, so I'm just gonna go ahead and draw that. It's not all E, so I don't have to worry about that. Got my 8-member ring with the methyls on opposite of the top bond, double bond. I just rearranged everything so it can get set, and then I'm gonna look at my chart, and I'm gonna go to the one, let's see, same conformation, more than 6 pi, and then I see we're dealing with heat. So it says methyl trans, but I don't have the same conformation, and I don't have, if this was E at the end, then we could deal with the same conformation, but it's not. Since this first one's different, I'm gonna do the opposite. So instead of doing, what was it, trans methyls, I'm going to do cis. So I'm gonna roll it around, and I'm gonna move this hydrogen down, move this methyl up, so I can keep it in the cis position. Okay, let's see if that worked. Okay, so these are the 2 E's. I haven't tried this out yet, but that's what I'm thinking. When you have E like this, you're gonna leave it. So that's just like a hypothesis, I guess. And let's see if it works. So I have 1, 2, 3, 4, 5, 6. I have a double bond, 2 going to 3, and then 4 going to 5. I'm gonna add my hydrogens, hit arrange and fit, and then lastly, I'm gonna make sure that they are E. So it looks right, because I got my highest conformation here, my lowest here, highest, so it's opposite, so it's good. And same thing with this one. I've got my highest priority on the opposite side of my other highest priority. Here goes nothing. Awesome. So far that works. I'm gonna still maybe play with it a little bit, but okay, so these aren't the same conformation, so I'm going to look at my chart and do the opposite. So I'm gonna go to where it says same conformation, more than 6, and I'm dealing with light. Same conformation, more than 6, light. It tells me I need to do methyl cis for the same conformation, so I need to do methyls trans for this conformation. And I could show you, like, it's a long process. Let me show you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I like doing my shortcut because I don't like dealing with all of these. I forgot to add my double bonds. I don't like to deal with all of this. So 2 going to 3, 4 going to 5, 6 going to 7, 8 going to 9. Okay, add my hydrogens, hit arrange and fit. And we have this monstrous chain. And then we have to go and move everything. Okay, so I undid the rearrangement, and now I'm gonna move stuff. So we have 2E, so I'm gonna put this on the top. I'm gonna have that like that, and then this one will be on the bottom. Okay, so I've got my E the right way, my Z, everything will be the same. Everything will be the same for the rest of them. So this is the only one that has opposites on for the highest conformations. And then what we would do, basically, use our heterolytic function to get this. Remember, we got it from this side, because if we got it from this side, you'd be connecting this carbon to this carbon, but we want this carbon to connect. We're gonna move it over here. I'm gonna go ahead and press arrange so we can start moving everything. So we're gonna start at the double bond next to the methyl because we don't want it next to the methyl. And now we start moving stuff. And you'll see at the end of this that we get the same thing that I've been drawing in my shortcut. So we get that 8-member ring, 3 double bonds, 1 on the top, and the methyl's opposite of that top double bond. And then I don't like the way that this bond looks, so I'm going to turn it on its side and try to move that hydrogen to the back, just so it looks a little bit better. Okay, so that's a long process, and that's why I really like doing the shortcut more. So when you have a deca, it makes an 8-member ring. When you have octa, it makes a 6-member ring. When you have hexa, it makes a 4-member ring, I believe, with 2 methyls on the bottom. So we have the same amount of carbons. We have 10. We just have 8 in the ring and then 2 methyls sticking out. Okay, so I'm going to go to the same conformation, more than 6 pi, and light. Methyl cis, so I want methyls trans. Because we're not dealing with the same conformation, we're dealing with different conformations. And then you'll see the little notes on the bottom that I have about if these two were E on the end, but these were Z, then it would be the same conformation. Since this one's different, it's not the same conformation. Even if you have 3 numbers and what the middle one's different, it's the same conformation. So I know it's going to be a long video. It's just a lot of information, and I want to show you guys the shortcut and the long way to do it. And then there's some exceptions as well. If they're all E, Okay, so this is a perfect example. So we have a Z in the middle, but we have the two E's on the outside. So this is actually going to be used as like the same conformation. We have octa, and remember I told you it's going to make a 6-member ring. So I'm going to make my 6-member ring. I have the same amount of carbons. Oops, same amount of carbons that would be in an octane. So I have 6 and then the 2 for 8. So everything's good. And then I'm going to add my hydrogens, arrange and fit. And lastly, I'm going to check and see. So I have 1, 2, 3, 4, 5, 6 pi rings. So I'm going to look for same conformation, 6 pi rings, and then heat. This means that my methyls are going to be cis, and that's what it looks like. So let's go ahead and try that out. I believe that if all of these were E, then we would leave it as is if we're dealing with heat. Again, I haven't done this enough to really, okay, so I see E. I've been making a ring. I'm just gonna leave it like this and see what happens. So I already put a double bond here, and then 1, 2, 3, I'll put a double bond here, and then 4, 5. I'm going to move these around because all of them are going to be, the middle one's going to be trans. Okay, so it should look something like this, and then I'll add my hydrogens, hit arrange. And I'm thinking that it wants this answer because this is actually more stable than making a ring, because the ring would be 4 members and then 2 methyls at the bottom. Okay, and I believe this is the same one, but we have Z conformation, and we know that Z is less stable, so that's why we want to make a ring with this. Hexa makes a 4-member ring, the double bond on top, and 2 methyls on the bottom. I'm going to add my hydrogens, hit arrange and fit, and then I'm going to go look at my chart, and I have same conformation, 6 pi, wait, I don't have any pi bonds. I have light. Oh, I do have 1, 2, 3, 4, 5, 6. So this one, I actually did it wrong. Since the pi bonds are on the ends, what we're going to do, so sometimes it's hard to visualize it when you only have, when you draw it like this. So sometimes when the pi bonds are at the end, there's not going to be methyls in the bottom, so this is actually going to make a 6-member ring. When the pi bonds start at 2, that's when you have methyls attached, but when you have 1, starting at 1, you're either going to make a 6-member ring, or you're not going to make anything because it's going to be E conformation. I'm not going to change the conformation because I'm going to change it around anyways and do my ring, and it won't matter at the end. And I don't believe you have to move things around, but I'll just go ahead and do it. So normally this would be done like this. Hit arrange and fit. And that should be good to go. Okay. So it takes a little bit of practice. I'll have all the trends on the bottom so you guys can look at it. I really, really hope that helps. I try to simplify as much as I can for this lesson. I think if you just have like a Word document with that open, I think it'll help. I try to put like little extra stuff on the bottom, like what happens if let me see, if the front number is different, if heat is reacting with something to make a 4-member ring, so things like that. So yeah, I'm hoping that with that you'll be able to do it. But good luck.